Hey everybody, this is Larry. This is day 5 of the Leetcode March Daily Challenge. Hit the like button, hit the subscribe button. Join me on Discord. Let me know what you think about this problem and today and general life. Yeah, so today is my last evening in Medellin. So I am not 100% sober, say, but let's face this problem together. I'm probably also doing my video tomorrow a little bit slow, so hopefully that's okay. Hopefully, it's not demanding, but I'll probably do it from New York, I believe, unless I don't know, unless things really, I don't know, I don't think so. But we'll figure out how it works. I mean, this is how async internet works, so I think we'll be okay, right? Yeah. So today's problem is delete and earn. So okay, let's see. What are we deleting? What are we earning? So okay, so we have three. Oh, I should actually read the problem. Yeah, like I said, I'm not 100% right now, so we'll see how that goes. But yeah, okay. So you give me the nums. You want to maximize. Okay, pick any num sub I and delete it to earn num sub I points. Afterwards, you must delete every element equals to num sub I minus 1. And okay, that's interesting. So basically, the idea is, I mean, this reminds me a bit of the dynamic programming problems in that, let's see, what is n? N is 2 times 10 to the 4th. So, but basically, the idea is that, for every number, only have two choices, right? Or every unique integer, you only have two choices, right? One is to keep the number, and the other is to not keep the number, right? And then skip it. So it reminds me of one of those, was it Robber problems or something like that. I'm just trying to also think whether we can be a little bit smarter. But let's see. Okay, so I don't. I mean, this is a weird one because it's supposed. I don't know. It's supposed to be a medium, but I think I have an idea, and like I said, it's gonna be like the I forget. I think on Leetcode they call robbers, but it's the idea that you can take A, and then when you take A, you cannot take A plus 1 or something like that, right? So that's basically the idea. And of course, in this case, there is a greedy component in that if you pick a number, you pick all instances of these number because it doesn't cost you any more, right? But in this case, you want to pick all the threes because why would you stop at 1 3? So that's basically the idea. Okay, so then the first thing I would do is, let's see, let's just have a counter is equal to collections, dot counter of nums. And then now we have, let's just say we have set of nums as, let's say we convert this to a list, and we sort this. I think we have to actually convert this to a list again, maybe I didn't need this list, but either way. So basically, this is my unique. How do you spell unique? Right, so here, right, so we have all these unique numbers and then we have it sorted. So now we have 4. Okay, that means that we can do two things. Yeah, so then now you go by every index, and this is now, I think, exactly the same as the robber problem. I call it the robber. I mean, that's the Leetcode one, right? So that means that you could do it bottoms up, you could do it tops down. I'm going to do it top down for now. Let's just say go of index, right? So then now, if index is greater than or equal to n, then we return 0. N is equal to length of length of unique, because that's the unique thing. And then now we can go, let's say, and this is dynamic programming at this point. Hopefully I made that clear, maybe not. My apologies, I'm not 100% right now. But basically you have two choices, right? One is take current index. So we take this. Tick is equal to this index times, or rather, let's see, what does that mean? This is, okay, yeah, this is the number, and then, so it's this times counter of unique of index, because that's the number of counter, because then you take all of them, and then this plus go of index plus okay, actually there is an additional if statement that I didn't make explicit, which is that unlike the robber problem, we should check that index plus 1, for example, okay, right, let's see. So current is equal to this thing, say, and then we do, okay, if index plus 1 is less than n, and unique of index plus 1 is equal to unique of index plus 1. Oops. So in this case, then tick is equal to current plus go of index plus 2, because now you want to skip the index plus 1, so you do index plus 2. Else tick is equal to current plus go of index plus 1, because that means that the next bigger number is already doesn't include plus 1. And of course the same logic applies to the robber problem, so we don't have to think about num sub I minus 1, because by default when we go from left to right going forward, that's the thing that you're going to do anyway. And then skip is of course just go of index plus 1, and that should be good. So then now we return max of tick and skip, and then that should be good. We go of index of 0. Is that true? I think that's just true. Yeah, so let's give it a run. Of course we didn't do the memorization part, so it may time out, but at least I want to make sure that I'll make sure that at least we return. These test cases are actually kind of terrible, so it may actually be good even if the answer is wrong. So let's just do something like funky, and then let's give it a run. Let's give it a spin. Yeah, still may time out like I said, and it should. So this looks good for now. What we want to do is do a memorization technique, right? Because n is really big. Even if they're all unique, it's going to be, I guess, 10 to the 4, which is what, 10,000. So the 10,000 numbers, if you don't memorize it, it's going to be a little bit sad. Here we can memorize it by just let's just say cache is equal to, I don't know, it doesn't really matter what this part is, n plus 1. No, I think n is probably fine. Maybe not. But hash cache is equal to 4 times n, right? So then now we just have to add some magic, which is if hash cache of index, return cache of index, and then here of course we go hash cache of index is equal to true, and then cache of index is equal to this thing, and then we can return the cache. Let's run it again real quick. I guess I should have showed an exponential case, but this doesn't even seem that much faster, to be honest, than before. But that's because we didn't really figure out how to scale it per se. So maybe we can do something like this. Now, because it's on the uniqueness, so this is a little bit awkward. Okay, fine. Let's just run it one more time and then we'll submit. Because the worst case is that all the numbers are unique, which I'm a little bit lazy to do. I mean, you could do something, right? For example, you can set nums is equal to list of x for x in range of was it 10 to the 4, so something like this. If you do something like this, then it should give you the example case. And obviously this is the wrong answer, but we only care about the running time, and you can actually check to see if the running time would run too slowly by commenting the caching part, and this should give you a time limit exceeded. And you can, yeah, I mean, it's going to go time limit exceeded. I'll be very shocked if it doesn't. And then here, like I said, if you run it, it was running in like pretty quickly. But as you should know, definitely remember to remove it and then one more time. Oh, well, okay, fine. Just to make sure that is right before we submit. I don't remember this problem. Have I done it before? I guess not, huh? So yeah, okay, but still, doesn't challenge me enough, I guess. Even so, several. I mean, I was a little bit slow, I suppose. But yeah, so the streak is now 704. Yay, yay, yay! And this is my first time solving this problem. Yay! It's been a while, so I feel like since they've given a problem that is new to me. But I'll welcome it anytime. So where's the complexity, right? Well, if all the numbers are unique, and also not sorted, then this is going to be n log n. So let's write that here. This is linear time, but this is going to be n log n, and that's going to dominate it. Yeah, let's just write oops, and O of n log n. And here the complexity for here, remember that index can go from 0 to n, or maybe n plus 1, something like that, but roughly 0 to n, which is O of n number of numbers of input. So each index is O of one space, because you just store it in, you know, two different things maybe, and each index is O of one time, because at most you're doing O of one lookups on all these things. So this is going to be linear space and linear time, and that's pretty much all I have for this one. Yeah, I mean, I haven't seen this one before, so I'm happy about this. Yeah, that's really all I have. Let's take a look at the show hint. We take a number, let's take it all. Yeah, I knew that. I wonder if this is the easiest problem. Keep track of what the value is of the subset of the input. I don't know. I am not 100% enough to read that. Okay, cool. That's all I have for this one. Yeah, stay good, stay healthy, take good mental health. I'll see you later. Bye-bye. Oops.